Okay, let's start. Today we are very happy to have Blake Woodworth from TTIC, Toyota Technical Institute of Chicago. Blake is a second-year PhD student working with NetCerebral, working on optimization and machine learning. Today he's going to talk about tight complexity bounds for optimization composite objectives. Okay.
Okay, thank you. Right, so as you said, I'm Blake, and this is joint work with my advisor, Nadi Cerebro. So I'm going to be talking about finite sum optimization, which is an optimization problem of the following form. So we've got an average of m component functions fi, and we're going to be using epsilon throughout the talk as the level of accuracy we want in terms of function value, not in terms of iterates. So this is a very well-studied problem. There's a wide range of examples of this appearing in practical situations. So there's kind of two different types. There's kind of the small m type where you have not that many functions that you're averaging. So for instance, maybe in a matrix optimization problem, you could have minimization over a L1 matrix norm and a spectral norm or something like this, and that would be two functions. In the larger M setting, this is frequently an ERM type objective. You've got data points C and Y, and your component functions are the loss of a particular weight vector x over that training example. For example, logistic regression, lasso problems have this sort of form. You could alternatively think of the regularizer as going in the being an extra function. Okay, so there are a whole bunch of algorithms currently that seek to exploit this sort of structure in the problem. So there's some deterministic algorithms like FISTA and ADMM, and prox accelerated gradient descent, which I'll talk about today, which are kind of tailor-made for the finite sum structure. There's also a wide range of randomized algorithms, particularly coming up in the past couple of years. SGD is not a new concept, but SAG, SDCA, SVRG, Saga, things like this are all kind of tailor-made for this problem. And there are ways of accelerating these algorithms, particularly by Lin et al. 15, that kind of generically get accelerated rates for these algorithms. And there's also a paper out of Princeton in the last year or two showing ways. So these algorithms are particularly analyzed for like the smooth and strongly convex case, and Alan Zhu and Azan present a way to reduce this non-smooth or non-strongly convex or both problems into smooth and strongly convex problems so that these algorithms can be applied there. So you guys are probably familiar with this, but just to clarify, so there's kind of this upper bound and lower bound, two different sides of looking at optimization analysis. So an upper bound is kind of a statement that for any I can come up with an algorithm such that for any functions at phi that you give me, I can find an approximate solution using some hopefully small amount of computation. On the other hand, we have lower bounds, which is kind of a statement for a class of algorithms. I can find functions at phi for which any algorithm in that class takes at least some other amount of computation. And they lower bound the best possible guarantee that any algorithm in that class can give. So in order to talk about the blank amount of computation, we need some model of computation. And in this talk, I'll be using an oracle model where one unit of computation is one query to this oracle. So the oracle returns the function value of a particular component at x, a gradient or subgradient of a component at x, and then the prox of the component function at x. What this means is it's kind of a side minimization problem, which trades off between minimizing the component and staying close to the query point x, where beta kind of controls this trade-off. So when beta is really small, it'll return the minimizer of the component, and when beta is very large, it'll just return x again. So sometimes this prox can be easy to compute. So for example, L1, L2 nuclear norms all have nice closed form prox functions, and also generalized linear functions can be computed fairly nicely. But it is not always easy to compute. So a general function fi is not, this optimization problem isn't necessarily easy. This is not of huge concern when talking about lower bounds, because we're saying even if you had this prox information, you still wouldn't be able to do any better than this. But for the upper bounds, that's something to keep in mind. And so today I'll mainly be talking about lower bounds for deterministic and also for randomized algorithms. And I want to emphasize that when I'm saying randomized algorithms, I'm talking about the algorithm that's flipping coins and not the oracle. So the oracle is always going to return exact gradients or subgradients and exact prox output. It's not, there's no noise in the oracle. And the questions I'm going to be addressing in particular are whether existing finite sum optimization algorithms are optimal, how do the deterministic and randomized algorithm optimal rates compare to each other, and how useful is this prox information? So when does it improve an algorithm's convergence rate? So previously, there's been a whole lot of lower bounds in optimization, particularly for single functions. There's a wide body of work and a whole bunch of different settings, different assumptions on the algorithms. Nesterov, Neverovsky, and Udin, et cetera. And they have something for most of these settings. In general, they tend to be for deterministic algorithms. There's not as much for randomized algorithms. There are also lower bounds for composite functions, but these are somewhat lacking in a couple ways. So most of them only, I think all of them only consider gradient information, which that's a more standard setting. But they only apply for smooth components usually. And when they consider randomized algorithms, which is rare, they greatly restrict the class of algorithms they consider. So for example, this Shalov-Schwartz citation I have, you get this component gradient information, but you don't get to know which component you are getting it from. So for instance, SAG would not work because the lower bounds would not apply to SAG because you need to know which component you're talking about at each point. And finally, the constructions in our lower bounds are kind of inspired by some communication lower bounds from Arjavani and Shamir last year. OK, so we talked about lower bounds with gradient approximate information, kind of a smooth and non-smooth, non-strongly convex and strongly convex functions, and for kind of the broadest possible classes of deterministic and randomized algorithms. So in particular, the class of deterministic algorithms I'm considering are all deterministic algorithms that use this oracle, and that's it. No other restrictions, and the same for randomized algorithms. So they're very broad, broadly applying lower bounds. So this is the table of results I'm going to be filling in throughout this talk. The highlighted portions are in some way new to our paper, and the other ones are kind of well established. So I'll talk about upper bounds first. So again, this is a statement that for any functions fi, the algorithm needs at most blank gradient and prox oracle queries to get an approximate solution. So in the smooth case, so just to be clear that these are all conditions on the component functions fi. So each component has to be either Lipschitz or smooth, and either strongly convex or on a bounded domain. Then on the left here, we've got conditions on the algorithm. So they're deterministic or randomized, and then upper and lower bounds. OK, so these are upper bounds we can get using accelerated gradient descent. So the process kind of goes, you calculate the component gradients of all m components, you average them, and now you have the gradient of capital F, the full function.
Your gamma is the Lipschitz constant.
Lipschitz on the gradient. Yeah. So So I guess two things to note about these algorithms is that they only use gradient information, so they're completely ignoring the prox, and also they're not really exploiting this finite sum structure at all, because they're just calculating the gradient of the full function using the components one at a time. And as you'll see, you can't actually do better than this. We could do the same thing in the Lipschitz case. We could use gradient descent, get bounds like this. And I guess the question is, can we use proxy information to do better than this somehow?
Even for one dimension, m is the number function.
This is like a dimension independent thing. So if you require the dimension to be small, then these bounds would not. Right. OK, so I guess the way we're going to do better by using prox information is what we're going to call prox accelerated gradient descent. The general idea is as follows. We take our not necessarily smooth component functions. We replace them with a smooth surrogate. So we take, it'll look like this. The exact formulation isn't super important, but the idea is that these functions are both close to the component functions, the original component functions, and they're also beta smooth. And they have the nice property that we can calculate their gradient using the prox oracle. So using this, we just do accelerated gradient descent on the surrogate functions using this gradient computation with the prox. And using a standard AGD analysis, we can, and setting beta to the right value, we can get MLB over epsilon convergence rate, which is better than standard gradient descent. Using a slightly different analysis, but the same process in the strongly convex case, we get that rate. So this is what ends up being the optimal rates for deterministic algorithms. I'll show you that later with lower bounds. In the randomized setting, we have a whole bunch of algorithms that can achieve these rates. There's accelerated versions of SAG, SDSCA, SVRG, many more things like this. Those get the rate in the strongly convex case, and then this Alan-Zhu and Hazan reduction can get us the non-strongly convex upper bound. And in the Lipschitz case, we can use the same smoothing technique. So we, instead of doing accelerated gradient descent on the smooth surrogates, we instead do accelerated SVRG or something of that form on the smooth surrogates, and we get the same rates, or the same type of improvement.
So those bounds are achieved by the algorithm you on the previous slide?
Yeah, so this general algorithm gets kind of these four upper bounds.
Okay, but let's go back to the general algorithm. Let me see. So does it need to compute the gradient or just solve the prox operator?
So here you actually, you never use the gradients of the components, only the prox.
Okay, you use prox, but you can always define the gradient in that way.
So this is the gradient of the surrogate. So I don't have oracle access to this. I need to use the prox to get to it.
You're just using that gradient into the accelerator.
Right, right. So it's a gradient algorithm using the prox to calculate the gradients is the, yeah. Okay, so now I'm going to talk about lower bounds for deterministic algorithms. I'm particularly going to focus on the case where the functions are not necessarily smooth and not necessarily strongly convex. I don't have time to do all of them. So this is probably the simplest one and maybe most enlightening. So, okay, so there's kind of two different ways in which we get to be adversarial in our construction. So we're going to make it so that there are useful directions and there are useful components. So the directions is going to be captured by these vectors VR. There's going to be this k+1 dimensional subspace of the ambient space in which the function operates. All other directions are completely meaningless to the functions. And we're going to design the functions so that the algorithm needs to learn all of these vectors VR in order to find an optimal solution. At the same time, we're going to make it so that only some of the components are useful at any given time, in the sense that querying the oracle of a particular function may or may not tell you anything about these vectors VR. And so the ones in which it does tell you about the vectors VR, those are the useful components, and the other ones are not. And we're going to have these 0, 1 variables delta IR, which essentially say, so if delta IR is 1, that means that function I is useful for learning about vector VR. And I'll explain that in a little bit more detail soon. Right. So the analysis is based on the idea that the algorithm needs to learn all k plus 1 directions by querying some useful component k plus 1 times. And when I say learn, I mean it needs to induce the oracle to return a gradient or prox that is has a non-zero inner product with one of these vectors VR. So the kind of the advantage we have here in the deterministic setting is we, the adversary, can always anticipate the next move of the algorithm. So before the algorithm ever begins, we know which functions it's going to query and in what order as it goes along. And we also know at what points it's going to query them. So since we can predict this whole thing before it starts, we can really imagine this as we get to make decisions as the algorithm goes along. So properly, you have to design these functions before the algorithm starts. But since we know what the algorithm is going to do, we really can effectively construct these functions on the fly, so long as they're consistent with all of the oracle responses we've given so far. That's kind of the constraint we're stuck with. So this is the function construction we're going to use. And I guess just to highlight, everywhere x appears, it's in an inner product with one of these vectors VR. So that it's essentially projecting x onto this small subspace. And that's the sense in which these directions are the useful ones. To explain the delta IR, it's nice to focus on one of these terms in the sum. So this is kind of the key to the whole construction. So we've got delta IR times this absolute value of a difference between two inner products. And what we want here is we want to give away little information about vector VR at this point. So what that means is we want to be able to give a subgradient that is kind of, we want the subgradient of this particular term to be 0. We want that to be an allowable response. And that happens in two situations. So sorry?
Is those VR orthogonal to each other?
Yeah, sorry. So all the vectors VR are orthogonal. Yeah, it's an orthogonal basis for the subspace. Right. So 0 is in the subgradient of this particular term if one of two things is true. If delta IR is equal to 0, then the subgradient is just 0. Alternatively, if the two inner products are equal, then 0 is also in the subgradient, even if delta IR is 1. So this isn't a full proof of this statement, but it ends up being true that the algorithm is going to learn these vectors in order. So it has to learn v0 before it learns v1. It has to learn v1 before it can learn v2, and so on, all the way through to vk. And if I don't know vt minus 1, and I don't know vt, by don't know I mean I have my iterates have 0 inner product with both of those vectors, then I can return a 0 subgradient from this term. So if you don't know both of the vectors, I don't have to tell you about either of them. And if I know about 1, if you know about vector VR minus 1, I can hide VR by setting delta IR to 0. So this kind of creates this trade-off where I want to hide these vectors VR. So delta IR is going to be 0 when I'm hiding VR. But at the same time, the sum of the delta IRs over I kind of controls how painful it is to not know VR. So I could hide VR forever by just setting all of the delta IRs equal to 0. But then this term would never appear in capital F, and there's no reason for you to need to learn it at all. And so the way we're going to balance the trade-off is actually setting half of the delta IRs equal to 1 and half of them equal to 0. So half of the functions are useful for learning VR, and half of the functions aren't. In order to kind of formulate this in a nicer way, we're going to define the concept of a round. So kind of an obvious statement is that as this algorithm is optimizing the function, it has to make some sequence of queries to the oracle of components in some order. And we're going to define a round to be a subsequence in which exactly m/2 unique functions are queried. So the first round begins with the first query and continues until half the functions have been queried. And so we're going to define VR and delta IR in terms of this. So VR, we're going to define to be orthogonal to all the points queried before round R. So what that means is that during round 1, these two are going to be both exactly 0 for all R greater than 2, I guess. And we're going to set delta IR equal to 0 if and only if Fi is queried during round R. So what that means is that if F is queried during round R, delta R equals 0. So this condition holds, and I can return a 0 subgradient for this term in the component. And kind of going back to the fact that we can anticipate the algorithm's actions, since I know the order in which they're going to be queried and at what points, I can set delta 8, 1, 3, 1, 1, 1, and 5, 1 to 0 because I know those are going to be queried in the first round. And I can set 2, 4, 6, and 7 all to 1 so that the functions you didn't query ended up being the useful ones. So then for kind of to finish the analysis, the optimum is located at this point because at this point, every inner product here is equal to b. So every absolute value is equal to 0. And this function being the sum of absolute values is non-negative, so 0 is its minimum. And as a result of this, as long as b and k are set appropriately, the algorithm has to learn all the VRs in order to be within epsilon of the optimum. And since it can only learn 1 VR per round, the number of oracle queries needed is the number of VRs, which is order k, times number of rounds, which is, sorry, that should be the number of queries per round, which is m/2. So it's order k times m. Turns out we can set k equal to approximately LB over epsilon. So that gives us our lower bound here.
So the number of queries is not exactly m/2, but it's at least m/2.
Right. So if it queries F1 10 times in a row, then only the first one really counts.
So where is the constraint on k? I don't get it.
It comes from here. So if I make k really large, then all the terms in this sum are kind of have negligible impact on the suboptimality.
Okay.
Um,
So in the end, you take k to be 1 over epsilon.
yeah.
So k here is k is what? K is the total.
K is
M is the total number function, right?
yeah. M is the number of component functions, and k is the dimension of this important subspace, or equivalently, the number of terms in the sum.
Okay. But that has to be less than the dimension, right?
Yeah, so the dimension is actually going to be about m times k. So the dimension is basically the complexity. So I'm orthogonalizing VR to each of your queries before round R. So I need...
This argument goes to like the dimension is growing with your is this the kind of the dimension keeps growing? Is this the infinite dimensional problem?
Because if your number of query larger than k, the dimension, then you can solve the problem in million.
Yeah. So that's similar. I think in this rough book we also have an example of with infinite dimensional.
Because in general you can do n or one of them solve.
Yeah.
And here, I didn't understand how you deal with the prox queries. I mean, the gradient queries, okay, that's
yeah.
fine.
So the proof for that is a little bit stickier, but it ends up being that.
Because if I can, with prox queries, I can learn about the VR much faster.
Yeah, so what ends up happening is you have this minimization of Fi and the regularizer. And when you query Fi during round R, this delta R equals 0. And you can separate this sum into the things you know and the things you don't know. And you can also separate the regularizer into things you know and things you don't know. And so you have this, if you look at the things you don't know, you have a whole bunch of inner products that are kind of at the bottom of the absolute value. And you have this regularizer that doesn't want to go away from 0. And so the minimization will pick the bottom of the absolute value again. So your x's won't. The minimization doesn't want x to move away from 0 in those components, and so it'll leave them at 0 in the directions of vectors you don't know yet.
So where is the regularizer? I thought we were minimizing the sum.
Right. So I'm talking about in the prox expression.
Oh, that's what you mean. But
yeah. Where are we now? Yeah. So here, this term can separate over.
But I can take beta equals 0 now. I'm allowed to do that.
So if you look at any particular since delta IR is 0, if I know only vectors VR minus 1 and below, this term could be 0, and all of the terms before R could be 0, and all the ones after R have no need
I see.
to become non-zero because they're, yeah. So it's all about the separability of the sum into the two disjoint sets. Things you know, things you don't know.
Yes, okay.
Okay. Cool. So that's lower bound for Lipschitz and non-strongly convex. We can extend. This lower bound actually implies a lower bound for the strongly convex case. You can make an argument like, well, if I could optimize bounded and Lipschitz function, then I could also optimize a strongly convex and Lipschitz function in this time. For the smooth case where the construction has to have smooth functions, the construction ends up looking very similar. All of those absolute difference terms are replaced with squared difference, and that's really the only difference. And k and b have to be said a little differently, but the general structure and the analysis are basically the same. And for the smooth and strongly convex case, like probably the most interesting to most people, we take the smooth and non-strongly convex case, we add a L2 norm to the end of it, and the kind of same analysis goes through.
This is a lower bound when you consider the using the gradient mapping, using the prox gradient mapping. Does that implement lower bound also for the just if you only require the gradient each time for the smooth case? That is there any discrepancies between this?
Yeah, so it ends up being that the smooth upper bounds are achieved by gradient methods, which means that the lower bound, since I'm giving you strictly more information, they still apply to this, right? So that what this is saying is that the prox information really isn't doing you anything in the smooth case. It's only in the non-smooth case that the prox helps. So yeah, so as you might notice, these upper and lower bounds are tight up to constant. You also might notice that the lower bounds for the deterministic algorithms are actually higher than the upper bounds for the randomized algorithms. So this is saying that for certain values of epsilon, at least. And what this is saying is that the randomized algorithms are somehow beating this construction. So this construction somehow doesn't work against randomized algorithms.
Well, there's a question because for the deterministic algorithm, for the batch, you need a deterministic. It's not necessarily batch. Each time you just query.
Yeah, so it can do anything it wants, really. It just has to have its plan figured out before it starts. It can't flip coins anywhere. So this could mean calculating full gradients, or it could mean using the intermediate component gradients in some predefined manner.
What I'm thinking is that if you treat the finite sum or average as just one black box function,
Yeah.
it just queries a gradient. You just query the gradient using accelerated gradient, or then the Lipschitz constant is actually the largest eigenvalue of the Hessian matrix, which may not be simply bounded by gamma smoothness of any function.
But
So
then you're outside the assumption.
You outside the assumption.
Yeah.
So
Yeah. Gamma
the components being smooth implies that the average is, the components being gamma smooth implies that the capital F is also gamma smooth.
Yeah.
Yeah,
But the capital F can be much more smoother.
right. It could be.
So that's why I think that's the missing.
Right.
The upper bound is actually much better than you would get for the individual bounds.
Yeah,
lots of cases.
in general.
In general. In
Yeah.
worst case, of course, this.
Right. So these it's important. You're right that these are for FI and not capital F. So
For capital, that would be the worst case upper bound.
right, that the worst it could possibly be. Right. Exactly. Okay, so the randomized upper bounds are beating the deterministic lower bounds. So I guess now let's talk about why that might be in the context of, again, the Lipschitz and non-strongly convex setting. So there are two reasons why the randomized algorithm is kind of defeating the construction from the deterministic case. So one is that we can't hide the useful components anymore. So in the deterministic case, we knew what the functions were going to be, what order they were going to be queried in. We knew which points they were going to be queried at. So we could set our deltas to be 0 for the first m/2 queries, et cetera. In the randomized setting, we have no idea what they're going to do. So they just query in a random order. This whole thing kind of falls apart. So that's a problem. The other problem is we can't really hide the useful directions in the same way as we could before. So first of all, we can't pick VR to be orthogonal to all the queries before round R because we don't know what the queries before round R are going to be. And secondly, we relied crucially on 0 being in the subgradient of this absolute difference when these are exactly equal, and in particular when they're exactly equal to 0 for ones we don't know. But if the randomized algorithm simply queries a random vector, say a Gaussian noise vector, with probability 1, both of these are going to be non-zero, and they're also going to be different. And so we're going to be forced to return a subgradient that points in the VR minus 1 minus VR direction. And that would be bad news for the analysis of the construction. So we have solutions for these. So the solutions for hiding the directions are actually a little bit easier. So we're going to replace all of the absolute differences with this kind of flattened out absolute difference, which means that those two inner products need to be significantly different by more than c in order for it to kind of jump out of the bottom of this. So as long as the difference between the inner products is less than c, then I can still return a 0 subgradient. And the same thing actually applies for the prox, it turns out. The other thing we're going to do, instead of orthogonalizing v to your queries, we're just going to pick them randomly in high dimensions. And when the dimension is large enough, the probability of having an inner product greater than c is going to be small. This does end up meaning that the dimension we require for our randomized lower bounds is going to be very large, basically on the order of the complexity that we get cubed. You can improve this by making additional assumptions about the algorithm. You can say, well, if the algorithm's iterates lie in the span of previous queries, then this gets improved quite a bit. I'm sure there are other ones you can make that would have a similar effect. Fixing the issue of hiding the components is actually a little bit trickier. So what we end up doing is, instead of having m functions that all operate on the same subspace, we split it into m/2 pairs of functions that are operating on different subspaces. So each pair of functions, fi1 and 2, have their own subspace, which is spanned by the orthogonal set vir. So now we have 2 subscripts on v. OK. This is the construction. If you squint at it hard enough, this looks kind of similar to what we had before. So if you add these two together, you've got kind of this first term, b minus x0, and then you've got this sum over all of the r's of something that's kind of like the absolute value of these inner products difference. I'm not going to go into the analysis of this too far. It actually ends up being pretty similar to the case where m equals 2. So the argument goes, we look at each pair of these functions individually, and we say it takes a certain number of queries to optimize one of these pairs of functions. And we make it so that you need to optimize many of these pairs of functions in order to optimize capital F. And it goes from there. And we're aided in the fact of when we make C very small, like order epsilon or smaller, this flattened out absolute value becomes very close to the actual absolute value. And we again get this mk sort of lower bound. But now k is the number of vectors we have, vir, is actually m times k now, or order m times k, because we have m/2 pairs of functions. So because of the factor of m, it actually ends up being that k is only lb over square root of m epsilon instead of lb over epsilon, as it was before. And we can make another separate construction that shows a lower bound of order m. In this case, this lower bound is actually only applying for m that is smaller than 1 over square root of m. So that means that this m is actually completely, that this term is never going to dominate in this lower bound. But in the other ones, it will. I should mention that you always, for upper and lower bounds in the randomized case, you always have SGD. So if the number of functions is really, really large, or if the accuracy required is low, then SGD will be better. You'll get, like, for Lipschitz and non-strongly convex, you'll get order 1 over epsilon squared instead of square root of m over epsilon for that. Just thought I should mention that. So, OK, for the Lipschitz and strongly convex lower bound, we again have this this argument that we used before, that this lower bound implies this one, because Lipschitz and lambda strongly convex functions can be viewed as just Lipschitz. You can just ignore the strong convexity. For the smooth functions, we use a construction that's similar to the Lipschitz and bounded functions. We replace these squared out absolute values with the flattened out quadratic. It's a little harder to write down because you need it to be smooth, and you also need it to stay close to the square, z squared itself. But the analysis is very similar. And then for the strongly convex case, we add a L2 norm at the end, and everything goes through. So, okay, so now the upper and lower bounds for the randomized algorithms are almost tight. They are kind of different in this m log 1 over epsilon versus m term. It turns out that this is actually a very small difference because the second term of these bounds is going to be the dominant one unless epsilon is in this kind of weird regime where it's not too small and not too large. So that ends up not being too troublesome. Another thing we can notice, so this is the upper and lower bounds are kind of the same, so I just got rid of the lower ones or the upper ones equivalently.
Do you believe the square? By the way, in practice, is m larger than n or smaller than n? Different practice? Yeah.
Depends.
Because if m less than n, then you have a kernel in the home. I mean, there is a subspace of solution. If each m is a function of a linear function,
Again, if m is less than n,
then you have a subspace of solution instead of one solution.
yes, okay.
So my question is, do you believe that is square n or square m?
Here,
Yeah.
n
Do you
being the
believe-
dimension, you mean?
Yeah.
N is the dimension.
Because usually n is smaller than m unless you have a kernel of solution.
It's at least, yeah, so it's definitely, yeah, it's probably at least square root of n. Because all of this analysis definitely breaks down if the dimension is too small. So that these only hold in kind of large dimension problems.
But wait, right now the lower bound proof doesn't work if n is of order m, right?
If n is what?
If n and m are linearly related.
Yes, well, yeah. Unless there might be values of epsilon for which it's okay, but in general, if n needs to be quite a bit larger than m.
But you think it's true even if n and m are of the same order?
I think,
The lower bound.
so if epsilon is 1 over square root of m, more or less, then the dimension can be linear in m. But if epsilon is very, very small compared to 1 over square root of m, then the dimension needs to be way bigger. So
So upper bound, you don't have this question.
No, upper bound you still have this question. Can you improve the m to n?
Yeah, so,
Yeah.
but yeah, that seems difficult. Upper bound, what do you think? Who cares? The dimensional number of n?
M right now empirical risk number of data.
Yeah. Can be close, like millions, similar.
But
Most
there are
really-
problems where m is much larger than n.
The most interesting case would be n and n also similar. Both are large. Both are very large. But the order is hard to say. Sometimes automatically.
But sometimes it is order of 10 or 100 difference, so
Yeah, definitely.
then n is still better.
So in like an ERM kind of setting, m bigger than n is like a pretty realistic assumption, I think. So you have more data than dimensions.
Not necessarily.
I mean, not always, but
For most of the sparse.
right. So in that case, then maybe not.
Larger feature, just so you can still generate the case. Say you degree to polynomial mapping or hashing or something. So in that case, basically, number of data, number of each features, they can both be large.
Yeah, can be large. Yeah. Yeah, what city is that? Even for some you can consider some nonlinear function separation, like a kernel, basically. Right? You just pop up them as a larger feature vector.
Yeah.
So this power of randomization is consistent from m to m squared roots.
Right. So across the board, you get this kind of square root of m savings when you use a randomized algorithm.
Of course, the one that was the guarantee is like expectation.
Yeah.
But how about for hyperbolic bound? For hyperbolic bound, I know for the linear convergence ones,
So
you will trivially get the same.
So all of these lower bounds here are, the way they're stated is that you need this many queries to get an epsilon approximate solution in expectation. But I can make that high probability bound by making the dimension get very big. So the only probability kind of analysis related in these are the likelihood that you randomly guess an iterate that's in the direction of one of these important directions. So as the dimension goes to infinity, the probability of that goes to 0. And so these can all be made high probability bounds too.
For the last one, you have this log 1 epsilon. You do not have log 1 epsilon in front of n. This is as I remember, is consistent with what Alec Agora and Leon Bateau's paper. Right? They had papers something like this.
Yeah. So what happened with their paper was it actually it didn't actually apply to randomized algorithms.
Yeah.
Yeah.
But then there's a Guanghui Lan has a paper. So you must saw it. He has a lower bound, but he also has the lower bound, but he has the log 1 epsilon on both.
Yeah. So his made the assumption that the algorithm's only randomness is in which component it chooses.
Okay.
So it's deterministic except for which component to query next. And which component to query next has to be decided from a fixed distribution a priori. So that's fairly restrictive.
So here, what's more general in your setting?
Here the algorithm can do anything, really just anything randomly. So it can pick components randomly, it can add noise to its queries, it can randomly, it can really do, the randomized algorithm class here is basically any algorithm you can think of that uses the oracle.
No restriction on the distribution.
No.
From that perspective,
So I'm inclined to think that the log 1 over epsilon is probably should be here. So there's this little gap.
For the practical algorithm we are using now, like that's the one I think with Line's assumption is we are actually only choose the order.
Right. So I'm inclined to think that the upper bounds are the right ones here, and the lower bounds are slightly off by. The constructions we use for this m term in front of it, they're all very, very simple. Here they're actually linear functions, and here they're quadratic functions, and they're very simple. Nothing very clever went into them. You could probably do better by coming up with a more clever construction for that term, and you could probably get the log 1 over epsilon in there somehow. So I'm inclined to think that the upper bounds are the right ones. But for Lan's paper, the analysis was facilitated by knowing the distribution over the components they would query.
And also, I think this construction, I noticed one change is he actually had a finite dimensional construction. His argument is not like in his paper say, it's basically he basically modified that argument. Say, if you give me dimension n, then he throws you a function immediately. That's it. There's no arguments n will change with your iteration go on. It's just a finite dimensional reference, straightforward.
Yeah. There's also Yossi Arjibani has a paper in NIPS, I think, this year that has lower bounds for, I don't remember which one, probably, it might just be the smooth and strongly convex setting, but that has n in the bound, so they use a completely different analysis technique, and I'm not sure how comparable the bounds are because I think they're not quite the same when the dimension equals my requirement. So it's hard to compare, but they have something like that in NIPS. Okay, so as people notice, we've got this kind of square root of m improvement by using randomized algorithms. We also, as I noted before, the algorithms that are achieving the lower bound in the smooth case are gradient-only algorithms, and the ones that are achieving the lower bound in the Lipschitz case are also using prox information in both randomized and deterministic case. So the prox is buying you. The prox is improving the bounds, but only when the functions are not smooth. So just to summarize, kind of many of the existing finite sum optimization algorithms are optimal. Prox AGD, HED in the deterministic case, and then accelerated SAG, SDACA, SVRG, SGD also in the large epsilon regime. Also, we've got this square root of m improvement from randomized algorithms, and lastly, the prox is only helping for non-smooth functions. So, yeah.
Have you tried the lower bound coordinate design?
I don't have anything at the moment.
Because I have a stupid paper, but I need to assume a lot of things to get any lower bound.
So
I'm just curious.
So if you're looking at a coordinate, yeah, so you could probably implement coordinate descent with this oracle if you were clever enough, but I don't think it would have very interesting things to say about the hardness of coordinate descent. But
Yeah, but then I think Lan's paper also has his lower bound in his paper said that's lower bound directly applied to coordinate descent. He started his paper is about some, but the construction he had is a Nistrov style. Each one you have a coordinate is that wow.
Yeah.
You can just use it trivially as a lower bound for coordinate.
And he assumed the function can only query in the linear spans of the previous string, and you can only randomize in the coordinate, something like this. Yeah, I'm saying those assumptions are to make.
yeah, so that assumption is actually not that important. Like, we didn't assume that, but if we had, it wouldn't really change anything. We just wouldn't, the dimension would be a little bit lower is the only real difference. So.